right now, sitting exactly where you are, in whatever light or darkness surrounds you, you are glowing. Your body, your warmth, is pouring out light this very moment. Light too low in frequency for your eyes to catch, but bright as day to the right camera. Everything warm glows this way. And more than 100 years ago, when physicists tried to explain that glow, the simple light shed by any warm object, using the finest theory they had, the mathematics handed them something impossible. It said, every warm thing in the universe should be radiating infinite energy. The way out of that catastrophe led somewhere no one expected, to the reluctant conclusion that light is not a smooth wave at all, but something granular, something you can count. Tonight we are going to find out why we believe that, and it is not the reason you were taught in school. The real answer was hiding, all along, inside the glow of something warm. Get comfortable and settle in. Hit subscribe if you're new here, because by the end of this, the quiet warmth of your own body and the light it is shedding right now will mean something it never meant before. Now, let's slowly ease into this. Part 1. The story you were told is backwards. There is a story you have almost certainly been told about how light became a particle, and it is wrong in a way that is far more interesting than the truth it hides. The story goes like this. Once upon a time, there was a puzzle in a laboratory, a strange little effect involving light and metal and electrons, and a young Einstein looked at it, scratched his head, and proposed a bold fix. He said that light must come in tiny particles, and that idea explained the puzzle, and that is why we now believe light is made of particles. It is a tidy story. It has a problem to solve, and a genius to solve it, and a neat arrow running from the problem to the answer. It is the version in most textbooks, and it is very nearly the reverse of what actually happened. The truth is that Einstein did not start with electrons. He did not start with metal. He did not start with any laboratory puzzle at all. By the time he wrote a single sentence about light knocking electrons out of a surface, he had already concluded, from a completely different line of reasoning, that light behaves as though it is made of separate, countable pieces. And the reasoning that got him there had nothing to do with the effect that now carries his name. It came from the study of heat. It came from the way a warm object glows in the dark. And it came, most strangely of all, from a careful argument about disorder, about the number of ways the universe can be arranged, an argument in which the word particle never appears until the very end, when it falls out of the mathematics on its own. Tonight we are going to follow that real path, and I want to be honest with you at the start about where it leads and where it does not. It leads to a firm, defensible answer to one question, the question on the screen in front of you right now. Why do we believe light is a particle? By the end of this, you will know exactly why, and it is not the reason you were given in school, but it leads only to the edge of a second, more fundamental question, and there it stops, because physics itself stops there. That second question is the one written on the thumbnail. What is light, really? We will arrive at that question having earned it, and we will find that more than 100 years after all of this was worked out, nobody, not Einstein, not anyone since, has been able to answer it in the ordinary way you can answer what is a stone, or what is a wave on water. There is a reason stories like this get flattened into something tidier than the truth. We like our discoveries to have a clean shape, a single problem met by a single insight, because that is how discovery feels when we look back on it from the far side, once the mess has been swept away. But the real work of physics almost never happens that way. It happens sideways, through a person worrying at a problem that nobody else thought was connected to the thing they were actually trying to solve. Einstein was not trying to explain electrons leaving a metal. He was trying to soothe a discomfort about the very shape of physics itself, about why one half of it counted discrete things, while the other half painted smooth, continuous fields, and he followed that discomfort into a thicket of thermodynamics, and he came out the other side, holding the particle of light, almost by accident. The tidy version robs the story of exactly what makes it worth telling, which is how strange and indirect the road to a great truth usually turns out to be. And it is worth saying, before we go any further, that nothing you are about to hear requires you to be a physicist, or to hold any equations in your head. Everything in this story can be understood by following a chain of simple, physical ideas, one link at a time, the way you would follow a good mystery. There is a crime, which is a glowing object doing something impossible. There is a false suspect, the tidy textbook explanation that everyone repeats. There is a detective who refuses to guess and insists, instead, on counting. And there is a resolution that answers the question we set out to answer, while quietly opening a larger one we cannot close. All you have to do is let each idea settle before the next one arrives, and let the whole thing carry you along at the pace of a slow evening. Before we go back in time, let me plant one more thing in your mind, gently, so that it is waiting for you at the end. The question we are chasing tonight, why do we believe light is a particle, is really a question about how belief works in science at all. We do not believe things in physics because someone important announced them, or because they are pleasing, or because we can see them directly with our eyes. Nobody has ever seen a photon the way you can see a stone. We believe what we believe because independent lines of evidence, arriving from different directions, using different methods, keep pointing at the same answer, until refusing to believe it becomes harder than accepting it. That is what happened with the particle of light, and it happened slowly, against real resistance, over about 20 years. So as we walk through this, notice how the belief actually gets built, not in a single flash of proof, but as road after road converges on the same strange destination. By the time we reach the end, you will not just know that light is a particle. You will understand the kind of thing that counts as knowing in physics, and why that kind of knowing can be both utterly convincing and still leave the largest question unanswered. So set the tidy story aside. Forget, for the next couple of hours, that you have ever heard the phrase photoelectric effect, because we are not going to meet it until much later, and when we do, it will not be the hero of the story. It will be a witness called to confirm something that was already suspected. The suspicion came first, and it came from an unlikely place. It came from the oldest kind of light there is, the light that pours out of anything hot enough to shine. To understand why that glow shook physics to its foundations, we first have to understand how completely, how justifiably confident physicists were, at the end of the 19th century, that they already knew what light was. Because they did know. They had a theory of light so successful, so thoroughly confirmed, that abandoning any part of it would have seemed like madness. And that theory said, without the slightest ambiguity, that light is a wave. To feel the size of what was about to break, you have to first stand inside the thing that was about to break it. You have to understand the wave theory of light, not as a quaint old idea that got overturned, but as one of the greatest triumphs in the history of human thought, a piece of physics so beautiful and so correct that it is still taught, still used, and still true today. That is where the real story begins, not with a particle, with a wave that seemed to explain everything, right up until the moment it explained something impossible. Part 2. Imagine you are a physicist in the year 1890, and someone asks you what light is. You would not hesitate. You would tell them that light is a wave, and you would say it with the quiet confidence of someone stating that water is wet. And you would have every reason for that confidence, because in the decades just before, a Scottish physicist named James Clerk Maxwell had done something that ranks among the most astonishing feats in all of science. He had taken three things that seemed to have nothing to do with one another: electricity, magnetism, and light. And he had shown that they were all the same thing, wearing different clothes. Before Maxwell, electricity and magnetism were separate curiosities. There was the way a rubbed piece of amber attracts a scrap of paper. There was the way a lodestone pulls on iron. There was the strange discovery that a wire carrying current can deflect a compass needle, hinting that the two were somehow linked. Maxwell gathered all of these threads together and wove them into a single, tight set of equations, and when he did, something extraordinary tumbled out. His equations predicted that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field, and that the two could chase each other through empty space, rising and falling in step. An electric ripple, giving birth to a magnetic ripple, giving birth to an electric ripple. On and on, traveling outward. He had discovered a wave made of nothing but fields, needing no substance to carry it, able to move through the emptiness of space itself. Then Maxwell did the thing that turns a good theory into an immortal one. He calculated how fast his wave should travel, using numbers that had been measured in laboratories, numbers about electricity and magnetism that had nothing to do with light. And the speed that came out of his equations was the speed of light, exactly, to within the precision anyone could measure. This could not be a coincidence. Light was not merely similar to his electromagnetic waves. Light was one of them. Light was an electric and magnetic field, oscillating together, rippling through space at that one specific speed. The color you see is just the frequency of the ripple, how many times per second the fields rise and fall. Red light is a slower oscillation, violet a faster one, and beyond both ends lie the colors your eyes cannot see, the infrared and the ultraviolet, the radio waves and the X-rays, all of them the same kind of wave, all of them light in the broad sense, differing only in how quickly they vibrate. Now, why was everyone so sure this was correct? Because light behaves like a wave in ways that are very hard to fake. Think about what waves do that nothing else does. When two waves meet, they add together, crest reinforcing crest, to make a bigger crest, but crest falling into trough to cancel out completely, leaving nothing. This is called interference, and you can see it with light. Shine light through two narrow slits and let it fall on a screen, and you do not get two bright lines. You get a whole row of bright and dark bands, the fingerprint of two sets of ripples overlapping, adding up in some places and cancelling in others. Only a wave does that. A stream of little particles would simply pile up in two heaps behind the two slits. The bands are the signature of something spread out and continuous, something that can be in two slits at once and interfere with itself on the far side. It is hard to overstate how complete this picture felt, and how much of the ordinary world it quietly accounted for. The colors swimming on the surface of a soap bubble or on a film of oil spread across a wet road are interference, light waves bouncing off the top and the bottom of a thin layer and adding or cancelling depending on how thick the layer is. The way a distant streetlight splays into little spikes when you squint at it through your lashes is diffraction, light bending around the fine obstacles in its path. The rainbow, the ring around the moon on a humid night, the faint fringe of colour at the edge of a sharp shadow, all of it was optics, and all of it was explained, down to the last detail, by treating light as a wave. Maxwell's theory did not merely survive its tests. It walked through them without a scratch, again and again, for decades. And there was something almost philosophically satisfying about it too, which made it all the harder to give up. A wave is a smooth, continuous, even-handed sort of thing. Its energy is spread out everywhere along its length, shared evenly, divisible without limit. You can have a little light or a great deal of light, and you can dim it as gently and continuously as you like, sliding the brightness down toward zero, with nothing sudden ever happening along the way. There are no jumps, no grains, no smallest possible amount of light. This continuity felt correct. It matched the way light seems to behave when you turn down a lamp or watch a sunset fade. Nobody had ever seen light arrive in lumps, so why on earth would anyone imagine that it did? There is more. Light bends around the edges of obstacles, spreading into the shadow the way ocean waves curl around the end of a breakwater. This is called diffraction, and again, it is a wave thing, a spreading out thing, something a hard little particle would never do. Every one of these behaviors was measured, checked, and confirmed. The wave theory of light did not just explain a few tricks, it explained the entire science of optics. Every lens, every rainbow, every shimmer of color on a soap bubble, and it did it with perfect precision. By the end of the 19th century, Maxwell's theory was regarded as one of the crowning achievements of the age, a finished cathedral of physics. Light was a wave, smooth, continuous, spread out through space, its energy flowing evenly like water from a tap. There was nothing lumpy about it, nothing grainy, nothing you could count. To suggest otherwise would have been to suggest tearing down the cathedral. And this is exactly why what happened next was so devastating. The wave theory was not overturned by some new experiment that no one had done before. It was broken by one of the simplest, oldest, most ordinary phenomena in the world, something humans had been staring at since before recorded history. It was broken by the glow of a hot object. When you take the most successful theory in physics, the theory that had unified light and electricity and magnetism, and you point it at a piece of metal heated until it shines, it gives you an answer. And the answer is not slightly off. The answer is infinity. The answer is madness. The cathedral had a crack running straight through its foundation, and the crack was hiding inside a campfire. Part 3. The glow that should have been simple. Here is something you already know without knowing that you know it. If you heat a piece of metal, it changes color. Start with a black iron poker and push it into a fire, and as it warms, it first begins to glow a dull, sullen red. Leave it longer, and the red brightens, then shades toward orange, then toward yellow. Push it hotter still, hotter than any ordinary fire, and the glow climbs all the way to a brilliant blue-white, the color of the hottest stars. Blacksmiths have read the temperature of metal by its color for thousands of years, long before anyone knew what temperature even was. The color tells you the heat. That is the whole trick, and it feels too obvious to be interesting. But sit with it a moment, because there is something genuinely strange buried in it. The color of the glow does not depend on what the object is made of. Iron, gold, tungsten, a lump of ceramic, a block of packed carbon. It does not matter. Heat any of them to the same temperature, and they glow the same color. The light coming off a hot object seems to have forgotten what it is made of, and remembers only how hot it is. That universality is a clue, a very large clue, because in physics, when something depends only on one quantity and ignores everything else, it usually means you are looking at something fundamental, something about the nature of heat and light themselves, rather than the particular stuff in front of you. And here is a thought to hold on to, because it makes the whole business more intimate than it first appears. Every object glows, not just the ones hot enough to shine visibly. You are glowing right now. Your body, at its warm living temperature, is pouring out light continuously, in the infrared, at frequencies too low for your eyes to catch but perfectly visible to the right camera, which is exactly how night vision goggles find a person in the dark. The walls around you glow. The ground glows. A block of ice glows, faintly, because even ice is far above absolute zero. Everything with any warmth at all is radiating, and the color of that radiation, whether it sits down in the invisible infrared or climbs up into the visible reds and yellows and whites, is set purely by the temperature. A cool thing glows low and dim in the infrared. A hot thing glows higher and brighter, its peak color climbing toward the visible and beyond. The glow of hot metal is not a special case. It is just the moment when an object gets hot enough that its glow finally rises into the narrow band of colors your eyes were built to see. So the black-body curve is not some laboratory abstraction. It is the rule that governs the light coming off every warm surface in the universe, from your own skin to the surface of a star. Getting it right was not a minor housekeeping task. It was a test of whether physics understood the relationship between heat and light at all, anywhere, for anything. To study this properly, physicists needed to clean the phenomenon up, to strip away every distraction and look at the glow in its purest form. So they imagined, and then built, a very particular kind of object. Picture a hollow box or cavity, its walls made of some solid material, and imagine heating the whole thing until it reaches a single, uniform temperature. Every part of it exactly as hot as every other part. Inside that sealed cavity, radiation bounces around, absorbed and re-emitted by the walls over and over, until it settles into a perfect balance with them, a state of thermal equilibrium. Now poke a tiny hole in one side. A little of that trapped radiation leaks out, and you can measure it. What leaks out is the purest possible sample of heat turned into light, and it carries a universal character. Its spectrum, the way its energy is spread across the different frequencies, depends only on the temperature of the cavity, not on the material of the walls, not on the shape of the box, only on the heat. Physicists call this black-body radiation, and that little cavity with its pinhole became one of the most important objects in the history of science. Now, what does that spectrum actually look like? Picture a graph. Along the bottom, running left to right, we lay out frequency, from the low, slow oscillations of red and infrared on one side, up to the fast, high oscillations of ultraviolet on the other. Up the side, we measure how much energy the glow carries at each frequency, how much of the light is coming out at each particular color. Plot the real, measured glow of a hot cavity, and you get a smooth, humped curve, like a hill. It starts low on the left, rises to a rounded peak somewhere in the middle, and then falls back down on the right. Most of the energy is concentrated near the peak, with less at the very low frequencies, and less again at the very high ones. It is one of the most carefully measured curves in all of physics, and it has a shape that any theory of light and heat must reproduce if it wants to be taken seriously. Two things about that curve were known before anyone could explain it, and both match your intuition about the glowing poker. First, as you raise the temperature, the peak of the curve slides toward higher frequencies. A cooler object peaks down in the low, red frequencies, which is why a barely warm poker glows dull red. Heat it more, and the peak marches up through orange and yellow toward blue, which is why the hottest objects glow blue-white. The peak follows the heat. Second, as you raise the temperature, the whole curve rises and the area underneath it grows, and that area represents the total energy pouring out. A hotter object does not just change color. It radiates more energy overall, a lot more, which is why standing near a roaring furnace is so different from standing near a warm radiator. Both of these facts were solid, measured, and waiting for an explanation. So here was the task, laid before physics, at the turn of the 20th century. Take the most successful theory you have, Maxwell's triumphant wave theory of light, join it to the equally successful science of heat, the thermodynamics and statistical mechanics that had been perfected over the previous century, and use the two together to predict this simple, universal curve. It should have been a formality. It should have been a routine calculation, the kind of thing you assign to a talented student. Everyone expected the answer to fall out cleanly, one more confirmation of theories already beyond doubt. Instead, when the calculation was done honestly, all the way to the end, it produced something that no glowing object has ever done, something that would have made every warm thing in the universe, including your own body, an impossibility. It predicted that the curve does not have a peak at all. It predicted that the glow climbs forever, without limit, into infinity, and nobody could see how to stop it. Part 4. The catastrophe hiding in a warm room. Let us actually walk through the calculation that broke physics, because you do not need any mathematics to feel where it goes wrong. You only need to follow two ideas, and then watch what happens when they collide. The first idea is about how many different waves can fit inside the cavity. The second is about how much energy each of those waves is allowed to carry. Put them together honestly, and the universe catches fire. Start with the waves inside the box. Radiation trapped in a cavity cannot be just any wave at all. It has to fit. Think of a guitar string, fixed at both ends. It can only vibrate in certain patterns, ones where the ends stay still, a single arch, or two arches, or three, and so on. The wave has to fit neatly between the fixed points. The same is true for the radiation rattling around inside our cavity. Only certain wavelengths fit properly between the walls, the ones where a whole number of half waves span the gap. Each of these allowed patterns is called a mode, a particular standing wave the cavity is able to hold. So far, so tidy. But now ask a dangerous question. How many of these modes are there? And here is the trouble. There is no limit to how short the wavelength can be. You can always fit a shorter wave, and a shorter one, and a shorter one still, packing more and more half waves between the walls. Shorter wavelength means higher frequency, so the allowed frequencies climb upward without any ceiling at all. And it gets worse, because the modes do not just keep going up, they get denser as you climb. When you count carefully how many distinct standing wave patterns exist in a small slice of frequency, you find that the number grows with the square of the frequency. Double the frequency, and you get 4 times as many modes crammed into the same slice. Triple it, and you get 9 times as many. The higher you go, the more thickly packed the possible waves become, and there is no end to the climb. High up in the ultraviolet and beyond, there is a practically limitless throng of modes, more and more of them the higher you look. On its own, this need not be a disaster. Lots of possible waves is fine, as long as most of them stay quiet, carrying little or no energy. Everything depends on the second idea, the one about how much energy each mode is allowed to hold. For that, physicists turn to one of the most trusted principles in the science of heat, called the equipartition theorem. It had been tested and confirmed across all sorts of situations, and it says something that sounds perfectly reasonable. When a system is in thermal equilibrium, energy gets shared out evenly among all the different ways the system can move or vibrate. Every mode, on average, gets the same portion of energy, an amount set only by the temperature. Hotter means more energy per mode, but at any given temperature, every mode gets the same share, and crucially, it does not matter what the frequency of the mode is. A low-frequency mode and a high-frequency mode each receive exactly the same average energy. Fair and equal, the same ration handed to every single mode. Now watch the collision. We have a number of modes that grows as the square of the frequency, climbing forever, and we hand each and every one of them the same fixed portion of energy. So how much energy sits at each frequency? It is the number of modes times the energy each one carries. The number of modes grows as the square of the frequency, and the energy per mode stays constant. So the energy at each frequency grows as the square of the frequency too, climbing higher and higher the further into the ultraviolet you look, with no turning point, no peak, no coming back down. And if you want the total energy inside the cavity, you have to add up the contribution from every frequency, all the way up. But the contributions keep growing without limit, so the sum does not settle on any number. It runs away to infinity. Take a moment to feel how insane this result is. The calculation says that a cavity at any temperature above absolute zero, a warm box, an oven, the inside of your own mouth, should contain an infinite amount of energy, most of it packed into impossibly high frequencies. It says that if you opened that little pinhole, you would be blasted not by a gentle glow, but by an unlimited torrent of ultraviolet and beyond. It says every warm object in existence should be radiating infinite energy right now. You, sitting there, at the warm temperature of a living body, should be an infinitely bright ultraviolet lamp. The chair should be, the walls should be, the whole world should have flashed into an infinite blaze the moment it rose above absolute zero. This absurd prediction earned a name that captures exactly how alarming it was. It was called the ultraviolet catastrophe, because the runaway happens at the high, ultraviolet end of the spectrum, and because catastrophe is not too strong a word for a theory that predicts every warm thing is an infinite furnace. Let us make sure the source of the disaster is crystal clear, because it will matter enormously later, when we watch Einstein reach into this exact machinery and change the one thing that was wrong. The catastrophe does not come from the counting of the modes. That counting is correct. There really are more and more standing wave patterns available the higher you go in frequency. And it does not come from the idea of sharing energy in equilibrium, which is also sound. The disaster comes from one specific assumption buried inside the equipartition theorem, the assumption that every mode, no matter its frequency, gets handed the same fixed portion of energy. That is the poisoned link in the chain, because if every one of those endlessly multiplying high-frequency modes really does get its full, equal ration of energy, then the total, summed over all of them, cannot help but run away to infinity. The modes multiply without limit, and each one draws the same salary, so the payroll is infinite. Reality, of course, does not do this, and the way you can tell, just by looking at a real blackbody curve, is that the high-frequency modes are clearly not getting their fair share. Up in the ultraviolet, where classical physics says the energy should be piling up fastest, the real curve has instead turned over and is falling towards zero. Those high-frequency modes exist, the counting is right, but they are somehow starved, receiving far less than their equal ration, and more starved the higher you climb. Something is rationing the energy of the high-frequency modes, holding it back, refusing to hand each one its equal portion. Nobody in classical physics could see what that something might be, because in classical physics there was no reason a high-frequency mode should be treated any differently from a low-frequency one. The universe was quietly enforcing a rule that the equations did not contain. Here is the part that made it impossible to shrug off. The same calculation, down at the low frequencies, works beautifully. If you compare the classical prediction to the real measured curve at the low, red end, they lie right on top of each other. The theory is not broken everywhere. It is exactly right at low frequencies and catastrophically, infinitely wrong at high ones. That is what makes it such a specific and revealing kind of failure. A theory that is wrong everywhere might just be the wrong theory, but a theory that is perfectly right in one region and produces infinity in another is telling you something subtle. It is telling you that one of your trusted assumptions is fine most of the time, and secretly false, in a way that only shows up when you push to high frequencies. Something in that chain of reasoning, the counting of the modes or the sharing of the energy, was quietly wrong. And whatever it was wrong in a way that reality had already quietly fixed, because real warm objects glow gently and do not incinerate the universe. The question was, what reality knew that the equations did not? Part 5. 2 half answers and the gap between them. When a beautiful theory gives an ugly answer, physicists do not immediately tear the theory down. First, they try to describe reality as it actually is, even if they cannot yet explain it. And by the end of the 19th century, there was already a description that worked, at least for part of the curve. It came from a German physicist named Wilhelm Wien, and it is worth pausing on, because Wien's contribution is one of those quiet pieces of the story that rarely gets told, yet without it, the whole later argument would have been impossible. Wien looked at the high-frequency end of the blackbody curve, the part that classical theory turned into a catastrophe, and instead of deriving a formula from grand principles, he found one that simply fit the data. He worked out a mathematical expression for how the energy is distributed across frequencies, and at the high-frequency end, it matched the measurements remarkably well. His formula had a particular shape. The energy rises with the cube of the frequency, but is then cut down hard by a factor that falls away extremely fast as frequency increases. a factor that also depends on the temperature. That steep fall-off is what tames the runaway. Instead of climbing forever like the classical prediction, Wien's curve rises, peaks, and then plunges back towards zero at high frequencies, exactly as the real glow does. There were two unknown constants in his expression, two numbers whose values had to be pinned down by experiment, but with those numbers in place, Wien's law traced the high-frequency slope of the real curve with real accuracy. So now physics had something strange on its hands, a kind of split screen. Down at the low frequencies, the classical calculation, the one built straight from Maxwell and equipartition, fit the data perfectly, while Wien's law drifted away from the measurements. But up at the high frequencies, it was the reverse. Wien's law hugged the data beautifully, while the classical calculation exploded into its catastrophe. Two different descriptions, each perfect in its own territory, each useless in the others, and between them, a stretch of the curve, the crucial middle where the peak lives, that neither one captured cleanly. It was as though someone had given you the left half of a face drawn by one artist and the right half drawn by another, and asked you to find the single hand that could have drawn the whole thing. It is worth dwelling on Wien's law a little longer, because it is going to become the secret hero of the entire story, and almost no version of this tale ever gives it its due. Wien's formula was not derived from any settled understanding of what light is. It was, in a sense, an educated fit, a mathematical shape that happened to trace the high-frequency data. But that is exactly what made it so valuable to Einstein years later. It was a reliable, experimentally grounded description of how the glow behaves at high frequencies, and it made no theoretical commitments about the nature of light one way or the other. It did not assume light was a wave. It did not assume light was a particle. It simply said, here is how the energy is distributed at high frequencies, as measured. When Einstein came to build his argument, this neutrality was priceless. He could take Wien's law as raw, trustworthy fact, feed it into his thermodynamic reasoning, and let the conclusion emerge without having smuggled in any prior assumption about what he would find. The half answer that seemed like a mere stopgap in 1900 would become, in 1905, the crucial piece of solid ground on which a revolution was built. And notice the region where Wien's law reigns, because it is telling. It works best at high frequencies and, relatedly, at low densities of radiation, precisely the regime where the classical wave picture fails most spectacularly. This is not a coincidence. The high-frequency end is where the graininess of light, whatever it turns out to be, matters most, because that is where the individual grains carry the most energy and are therefore the least wave-like, the least smooth, the most stubbornly discrete. Down at low frequencies, the grains are so small and so numerous that they blur together into something that looks, for all practical purposes, like a smooth, continuous wave, which is why the old classical calculation works so well down there. But up at high frequencies, the grains are large and few, and their discreteness starts to show. Wien's law, without anyone realizing it at the time, was a description of light in exactly the regime where it behaves least like a wave and most like a swarm of separate things. This is the moment to appreciate just how uncomfortable a position this was. In physics, having two partial laws that each work in a different regime is not a triumph. It is an accusation. It is nature telling you that there exists a single, more fundamental law underneath, one that becomes Wien's law when you push to high frequencies and becomes the classical result when you drop to low ones, and that you have simply failed to find it. The two half answers were like two footprints leading in from opposite edges of a field, and everyone could see that a single traveller had made them both, and no one could yet make out the traveller. Somewhere there was one formula, one curve, one idea that would reproduce the entire spectrum from the lowest red frequencies to the highest ultraviolet ones in a single stroke and match the measured hump in between. Finding it was the great problem of the hour. You may be wondering why any of this felt urgent, why grown physicists lost sleep over the exact shape of the glow from a hot box. Part of the answer is practical. Understanding how hot objects radiate was tied to real industrial questions of the era, to the efficiency of lighting, to the science of measuring high temperatures, to the German physics institutes that were built partly to serve a growing electrical and lighting industry. But the truer reason was pride, in the best sense. The black body spectrum was a place where the two greatest theories of the century, the theory of light and the theory of heat, were forced to speak to each other and give a single, definite prediction. If they could not agree on something as basic as how a warm object glows, then the confidence physicists felt in those theories was, at least a little, an illusion. The stakes were not really about furnaces. They were about whether the foundations everyone stood on were as solid as they seemed. And the honest answer, hiding in that humble curve, was that they were not. And notice what the problem really was, underneath the mathematics. It was not, at bottom, about finding a formula. Anyone clever enough could probably fiddle with functions until they found one that happened to fit. The real problem was that the classical calculation had seemed airtight. Every step in it, the counting of the modes, the sharing of energy according to equipartition, was built on principles that had been confirmed again and again in other settings. There was no obvious place to intervene, no loose bolt to tighten. To get a formula that fit the whole curve, someone was going to have to reach into that chain of trusted reasoning and change something that everyone believed was correct. They were going to have to break a rule and not know, at first, which rule they had broken or why breaking it was allowed. The person who did it was not a young radical looking to overthrow physics. He was a cautious, conservative, thoroughly respectable German professor in his 40s, a man who revered the classical framework and wanted nothing more than to defend it. His name was Max Planck, and he had spent years thinking about heat and radiation and entropy. When he finally found the formula that fit the entire blackbody curve, from end to end, with a precision that was almost unnerving, he was thrilled. And then he made the mistake of asking himself why it worked. The answer he was forced to accept horrified him, and he would spend much of the rest of his life trying to explain it away. He had found the single traveler who made both footprints. But the traveler, it turned out, was walking on ground that no one in classical physics had known was there. Part 6. Planck's Act of Desperation. Max Planck was not the sort of man you would cast as a revolutionary. He was orderly, formal, a lover of the great classical structures of physics, the kind of scientist who trusted the old foundations precisely because they had held up so well. When he turned his attention to the blackbody problem in the 1890s, his goal was thoroughly conservative. He wanted to understand the glow of hot objects using the tools he already had, above all the concept of entropy, and to show that the beautiful edifice of classical physics could account for it. He had no wish to break anything. He wanted to reinforce. For a while, he worked on the relationship between the energy in the radiation and its entropy, its disorder, trying different mathematical forms and seeing which one led to a spectrum that matched experiment. And in the autumn of the year 1900, guided partly by new measurements that were probing the low-frequency end more carefully than ever before, he found it. He wrote down a single formula for the blackbody spectrum, and when it was compared against the data, it worked everywhere. At high frequencies it melted smoothly into Wien's law. At low frequencies it slid just as smoothly into the classical result, and through the difficult middle, across the peak that neither half-answer had captured, it traced the measured curve with an accuracy that was almost unnerving. Planck had found the single traveler. He had the formula the whole field had been chasing. But Planck was too good a physicist to be satisfied with a formula that merely fit. He wanted to know why it fit, what had to be true about the world for this particular curve to be the right one. So he went digging into the foundations of his own result, trying to derive it from the statistical principles of heat. And it was there, in the derivation that he ran headlong into the thing he could not avoid. To make the mathematics produce his formula, he found he had to do something that made no sense inside classical physics. He had to assume that the energy exchanged between the walls of the cavity and the radiation could not take just any value. It could not flow continuously, in any amount, the way a wave should be able to give and receive energy. Instead, it had to come in discrete little packets, whole number multiples of a basic unit, 1 packet, or 2 packets, or 3, but never 1.5. And the size of each packet was not fixed. It was proportional to the frequency of the radiation. High-frequency light had to trade energy in big packets, low-frequency light in small ones. The energy of a single packet was the frequency multiplied by a new constant of nature, a tiny number that had never appeared in physics before, and which we now call Planck's constant. Think about how alien this was. In classical physics, energy is smooth. A wave can carry any amount of it and can hand it over in any quantity you like, a trickle, or a flood, or anything in between. That smoothness was not a minor feature. It was woven into the entire structure of Maxwell's theory and all of mechanics. And here was Planck, forced by his own successful formula to declare that energy is not smooth after all, that it comes in indivisible grains, and that the size of the grain depends on the frequency. He introduced this idea reluctantly, almost with an apology. He later described it as an act of desperation, and he meant it. He said he was willing to sacrifice any of his previous convictions about physics to find an explanation that worked, because after so many years of struggle, a solution had to be found at any cost. This was not the language of a man announcing a discovery he was proud of. It was the language of a man who had been cornered by his own equations and forced to sign something he did not believe. Look closely at what the packets actually accomplish, because it is elegant, and it is the exact repair the catastrophe needed. Remember that the disaster came from every mode drawing the same equal ration of energy, no matter how high its frequency. Planck's packets break that equality in a subtle and beautiful way. If a mode can only accept energy in whole packets, and if the size of the packet grows with the frequency, then a high-frequency mode faces a problem. To get even 1 packet of energy, it needs a large lump, because its packets are big. But in a system at a given temperature, large lumps of energy are rare. They are hard to come by. The thermal jostling only occasionally musters enough to deliver one. So the high-frequency modes, needing big packets they can rarely afford, mostly sit empty, starved of energy, exactly as the real curve demands. The low-frequency modes, whose packets are small and cheap, fill up easily and get their full share. The packets, in other words, are precisely the rationing mechanism that reality was using and the classical theory lacked. They explain why the high-frequency modes are starved, why the curve turns over and falls instead of running to infinity. The catastrophe is cured, not by changing the count of the modes, but by making energy lumpy, so that the expensive high-frequency modes usually cannot afford even their first bite. That is the real reason Planck's desperate assumption worked, and it should give you a shiver of recognition, because it is the first appearance of an idea that would eventually reshape all of physics. Energy, at least in its exchange, is not infinitely divisible. It comes in smallest units, and the size of the smallest unit depends on the frequency. This is the seed of quantum theory, planted, reluctantly, by a man who wanted only to save the classical world, not to end it. Planck had cracked the door. He just could not bring himself to walk through it, and he spent years afterward trying to find some way to close it again, to show that the packets were an illusion, a mathematical convenience, something that would eventually dissolve back into good old continuous physics. He never managed it. The door stayed open, and someone younger and less afraid was already stepping toward it. And here is the subtle, crucial thing about what Planck actually claimed, because it is where he stopped short and where the door was left open for someone bolder. Planck did not say that light comes in packets. He was far too cautious for that. In his mind, the graininess was a property of the exchange, of the handshake between matter and radiation. The walls of the cavity were made of little oscillating charges, tiny vibrating pieces of matter, and it was those oscillators, those bits of matter, that could only give up or take in energy in whole packets. The light itself, the electromagnetic field filling the cavity, Planck still imagined as a smooth, continuous Maxwellian wave. The chunkiness lived in the walls, in the way matter emits and absorbs, not in the light. He had put the quantum into the world, but he had quarantined it, sealed it inside the process of emission and absorption, hoping to keep the wave nature of light itself untouched. He had lit the fuse, and then tried to hold the explosion in his hand. For 4 years, the fuse burned quietly. Planck's formula was accepted because it worked, and the strange assumption behind it was mostly set aside as a mathematical trick, a bookkeeping device that no one needed to take too literally. Physics could use the formula without swallowing the philosophy, and perhaps it might have stayed that way for a long time, the quantum kept politely in its box, if not for a young man working as a clerk in a patent office in Bern, Switzerland, a man with no university position, no laboratory, no famous mentor watching over him. He had been reading Planck's work, and he had been thinking about entropy and radiation on his own, and he was about to ask a question that Planck had carefully avoided. He was going to ask, what happens if the graininess is not in the walls at all? What happens if it is in the light? And he was going to answer that question not by guessing, but by counting. Part 7. The most misunderstood paper in physics. In the year 1905, a 26-year-old named Albert Einstein, working 6 days a week as a technical examiner in the Swiss Patent Office, published a paper that he himself singled out as special. He wrote a letter to a friend that year, describing several pieces of work he had underway, and of one of them, and only one, he used the word revolutionary. It was not the paper on the nature of space and time that would later make him a household name. It was this one, the paper about light. He called it very revolutionary, and he was right, though it would take the rest of the physics world nearly 2 decades to catch up to just how right he was. The paper has a title that tells you, if you read it carefully, that this is not the story you were expecting. It is called, roughly translated, On a Heuristic Viewpoint Concerning the Production and Transformation of Light. Notice that word, heuristic. It is a careful, modest word. It means a useful guide, a fruitful way of looking at things, a viewpoint that helps you find your way, rather than a final claim to have proven exactly what light is. Einstein chose it deliberately. He was not going to announce that light is definitely made of particles. He was going to offer a viewpoint and then show that this viewpoint leads somewhere, that it makes predictions, that it earns its keep. And notice the rest of the title too. It is about the production and transformation of light in general. It is not about metals. It is not about electrons. The famous effect that would later be attached to this paper is barely in it, tucked near the end as one application among several. Because here is what almost no one who repeats the textbook story realizes. Einstein's paper does not begin with any experiment at all. It does not open with a laboratory puzzle crying out for a solution. It opens with a philosophical unease, a sense that something was structurally wrong at the heart of physics, and the something that bothered him was a mismatch, a strange inconsistency in the way physics described the world. On one side, there was the physics of matter. When you describe a gas, a box full of atoms and molecules, you describe it as a collection of a finite number of little things, each with a definite position and a definite velocity. The description is granular, countable, made of discrete pieces. You could, in principle, list them all. On the other side, there was the physics of light, Maxwell's theory, and it described light in a completely different language. Light was not a collection of countable pieces. It was a continuous field, a smooth quantity defined at every single point in space, with no gaps, no grains, infinitely divisible. Einstein looked at these two descriptions sitting side by side in the same physics, the granular one for matter and the continuous one for light, and he found the contrast suspicious. He called it a profound formal difference between the theoretical pictures of gases and of radiation. Why should the two great halves of physics speak such different languages, one counting discrete atoms, the other painting smooth fields? It felt to him like a seam in the world, a place where two pieces had been stitched together that maybe did not fit as neatly as everyone assumed. And rather than let that unease sit, he decided to probe it, to see whether light, when examined carefully, might turn out to be more granular, more matter-like than Maxwell's continuous picture allowed. This instinct of Einstein's is worth pausing on, because it is the quality that set him apart, more than raw cleverness. Plenty of physicists were cleverer with equations than Einstein was. What he had, to an almost uncanny degree, was a nose for which inconsistencies mattered. Physics is full of little mismatches and loose ends, and most of them are nothing, artifacts of approximation, things that will sort themselves out. The rare gift is to look at a particular loose end and feel, correctly, that it is not a loose end at all, but a thread that, if pulled, will unravel something enormous. The mismatch between granular matter and continuous light was, to almost everyone, simply the way things were. Two different kinds of physics for two different kinds of stuff. No more troubling than the fact that a river and a mountain are described differently. Einstein looked at the same mismatch and felt that it was a wound, that nature would not really be built with such a seam down the middle, and that the resolution would have to be light, becoming more like matter, more countable, more discrete. He was pulling the thread before he had any proof it would give, and the method he chose to pull it with tells you something about the shape of his mind. He would not argue about what light is. He would refuse, on principle, to start from any picture of light at all, wave or particle, because starting from a picture is how you fool yourself, how you end up finding only what you assumed. Instead, he would corner the light. He would surround it with facts it could not escape, the measured shape of its own glow and the iron logic of thermodynamics. And then he would ask it a question so sharp that its answer would reveal its nature, whether it wanted to or not. He was setting a trap, made entirely of things everyone already agreed were true, and he was going to let the light walk into it. Now, how do you probe such a thing without just guessing? This is the part that reveals Einstein's genius, and it is completely different from the tinkering guesswork that the textbook story implies. He decided that he would not assume anything about what light is made of. He would not start by declaring that light is particles and then look for confirmation. Instead, he would take the facts that were most solidly established, the ones no one doubted, and he would follow them wherever they led, even if they led somewhere uncomfortable. And the two facts he chose to trust were these. First, the measured shape of the blackbody spectrum, especially at high frequencies, where Wien's law described the data so well. Second, the most general and powerful principle available about systems in equilibrium, the second law of thermodynamics, and in particular, the profound interpretation of it that had been given by the Austrian physicist Ludwig Boltzmann, the interpretation that connects entropy to counting. So Einstein set himself a very particular and very clever task. He would take the well-measured behavior of blackbody radiation, feed it through the machinery of thermodynamics and Boltzmann's statistical understanding of entropy, and see what that machinery revealed about the hidden structure of light. He would let the light's own thermal behavior confess its nature. He was not going to look at light through a microscope, because no microscope could show him. He was going to interrogate its entropy, its disorder, and ask that disorder a single sharp question. If you behave the way you behave when I heat you and let you spread out, then how many things are you really made of? To understand the astonishing answer, and to understand why it counts as an answer at all, we first have to understand the tool he was reaching for. We have to understand what entropy actually is, and why Boltzmann's way of thinking about it turned it into something that could count the uncountable. Part 8. What entropy is really counting. Entropy has a reputation for being difficult, even forbidding, but the idea underneath it is one of the most intuitive in all of physics, and Boltzmann's great gift was to make that intuition exact. So let us set the equations aside completely and think about what entropy really means. Because everything that follows, everything about how light confessed its nature, depends on getting this one idea into your bones. Entropy is about counting. It is about how many different ways there are to arrange the tiny, hidden pieces of a thing, while keeping its large-scale appearance the same. Picture a can of paint, half filled with red pigment, half with blue, the two lying in separate layers, red on the bottom, blue on top. Now stir. As you stir, the red and blue swirl together, and after a while, you have a uniform purple, the same shade throughout. Here is the question that unlocks entropy. Why does stirring turn the separated layers into uniform purple, and why does no amount of stirring ever turn uniform purple back into separated layers of red and blue? Nothing in the laws of motion forbids the unmixing. If you could somehow reverse the exact motion of every particle, the purple would obligingly separate back into red and blue. So why does it never happen on its own? Boltzmann's answer is beautiful and simple. It is a matter of counting arrangements. Think of all the possible ways the individual specks of red and blue pigment could be positioned in the can. There are, it turns out, an almost incomprehensibly large number of arrangements in which the red and blue are thoroughly intermingled, so that at every scale your eye can see, the paint looks evenly purple. And there are, by comparison, only a tiny number of arrangements in which all the red specks happen to be gathered in the bottom half and all the blue in the top. Both the purple and the separated states are made of the same specks. There are just vastly, overwhelmingly more ways to be purple than to be separated. So when you stir and let the specks tumble into some arrangement more or less at random, they land, with near certainty, in one of the astronomically more numerous purple arrangements. The separated state is not forbidden. It is just so rare, so vanishingly outnumbered, that you would wait longer than the age of the universe to stumble into it by chance. That is entropy. The entropy of a state is a measure of how many microscopic arrangements correspond to it, how many ways the hidden pieces can be shuffled while the visible whole stays the same. A state with many possible arrangements has high entropy. A state with few has low entropy. And the reason things evolve from order toward disorder, the reason the arrow of time points the way it does, is simply that there are more ways to be disordered than ordered, so a system left to itself drifts, overwhelmingly likely, toward the arrangements there are more of. Boltzmann captured this in a single relationship, one of the most important in all of science. He said that the entropy of a state is set by the number of microscopic arrangements that produce it, growing as that number grows. More ways to arrange, more entropy. It sounds almost too simple to be profound, and yet this one idea explains why heat flows from hot to cold, why perfume spreads across a room, why the past is different from the future. There is a phrase worth carrying with you from here on, because it captures the whole trick in a handful of words. Entropy is the universe keeping count. Every time you see something spread out, mix, cool down, or fall into disorder, you are watching a system drift toward the arrangements there are simply more of. The disorder is not a force pushing things apart. Nothing is pushing. It is pure arithmetic, the overwhelming numerical advantage of the messy states over the tidy ones, playing out with the reliability of a law. And because it comes down to counting, entropy carries information about the countable pieces underneath. If you know how a system's entropy behaves, especially how it changes when you give the pieces more room, or less, you are, in effect, reading a report on how many pieces there are and how freely each can be placed. The entropy is a window onto the hidden inventory. This is the property Einstein was about to exploit, and it is why entropy, of all things, could serve as a tool for counting the uncountable. Boltzmann, it should be said, paid a heavy price for this idea. In his own lifetime it was fiercely resisted, in part because it rested on the reality of atoms, and many respected physicists of the late 19th century still doubted that atoms were real, physical objects rather than convenient fictions. Boltzmann insisted that the counting of arrangements only made sense if there really were discrete things to arrange, actual atoms and molecules, countable in principle. He fought for this view against powerful opponents, and it wore on him. He did not live to see how completely he would be vindicated, or to see a young patent clerk take his statistical vision of entropy and use it, of all the audacious things, to prove that even light, even Maxwell's sacred continuous wave, must be built of countable pieces too. Boltzmann's tool for counting atoms was about to count the grains of a sunbeam. Let us do one more example, because it is the one that matters most for what is coming. Take a sealed room and a small puff of gas, just a handful of atoms, released in one corner. What happens? The gas spreads out to fill the whole room, always. And once it has filled the room, it never spontaneously gathers itself back into the corner. Why? The same counting logic. There are relatively few arrangements in which all the atoms are clustered in one small corner, and a colossally larger number of arrangements in which they are spread throughout the entire room. So the gas, tumbling through its possible arrangements, drifts inevitably toward the spread-out state, simply because there is so much more of it to drift into. And here is the part to hold on to. The bigger the room, the more room there is to spread into, the more possible arrangements there are, and so the higher the entropy of the spread-out gas. The entropy of a gas depends on the volume it occupies, and it does so in a very specific mathematical way, a way tied directly to how the number of possible arrangements grows as you give the atoms more space. That relationship between the entropy of a gas and the volume it fills has a particular fingerprint, a particular shape, and it is a fingerprint made possible entirely by the fact that a gas is a collection of separate, countable atoms, each one free to be anywhere in the available space. Now hold that thought against the problem Einstein faced, and feel the difficulty of it. He wanted to apply this counting of arrangements idea to light. But light, in Maxwell's picture, is not a collection of separate countable atoms. It is a smooth, continuous field, spread through space, with no grains, no pieces, nothing discrete to count. When you ask how many ways you can arrange the pieces of a continuous wave, the question seems to have no answer, because there are no pieces. So how could entropy, a concept built entirely on counting discrete arrangements, apply to light at all? What, in a smooth, continuous wave, is there to count? This was the impossible-looking gap Einstein had to cross. And the way he crossed it was to stop asking what light is, and instead to measure, very precisely, how the entropy of light behaves, and then to look at the fingerprint that behavior left behind. Because if the entropy of light carried the fingerprint of countable pieces, then, whatever Maxwell's smooth equations said, the light would be telling him, in the language of thermodynamics, that it was secretly a crowd. Part 9. Slicing the light into bands. Let us gather ourselves for a moment before we follow Einstein into the heart of his argument, because we have covered a great deal of ground, and the next steps are the most important in the whole story. Here is where we stand. Physics had a crisis, a warm, glowing object that the wave theory of light said should radiate infinite energy. Planck had patched the crisis with a formula, but the patch required energy to come in packets, and Planck had hidden those packets in the walls of the cavity, refusing to let them touch the light itself. Einstein, uneasy about the split between granular matter and continuous light, had decided to interrogate the light's entropy directly, using Boltzmann's insight that entropy is really a count of hidden arrangements. And we ended on the puzzle. A continuous wave has nothing to count. So how can it have the entropy of countable things? Einstein's solution begins with a move that is so natural you might almost miss how clever it is. He took the blackbody spectrum, that smooth, humped curve of energy spread across frequencies, and he mentally sliced it up. Imagine taking the frequency axis and dividing it into a great many narrow strips, each strip covering only a tiny range of frequencies. Within each strip, the light is very nearly a single pure frequency, a single color, and each strip carries a small portion of the total energy, and correspondingly, a small portion of the total entropy. Einstein treated each of these narrow frequency bands as its own little subsystem, a small parcel of radiation that could be studied on its own. The whole glow, then, is like an orchestra, and he has separated out each section, each narrow band of pitch, so he can examine them one at a time. The total energy is just the sum of the energies in all the bands, and the total entropy is the sum of all their entropies. Why slice it up at all? Because a single, smooth, continuous curve is hard to reason about as a collection of parts, and Einstein needed parts. He needed subsystems he could compare against one another, that he could move energy between, that he could ask questions about individually. By cutting the spectrum into narrow bands, he turns one indivisible glow into a great many small, nearly pure parcels of light, each almost a single color, each with its own little store of energy and entropy. It is the move a good thinker always makes with something continuous and overwhelming. Break it into manageable pieces you can hold one at a time. And notice that this slicing does not assume anything about whether light is a wave or a particle. A band is just a range of frequencies. Both a wave picture and a particle picture agree that light has a spectrum spread across frequencies, and that you can consider a narrow slice of it. So Einstein has committed to nothing yet. He has simply arranged the light on a workbench in a way that lets him interrogate it piece by piece. Now he makes his key assumption, and it is a modest, reasonable one. He assumes that the entropy carried by any one band depends only on two things: how much energy is sitting in that band and what frequency the band is at. That is all. The entropy of the red band depends on the energy in the red band and on the fact that it is red. The entropy of the blue band depends on the energy in the blue band and on the fact that it is blue. Each band minds its own business, its disorder set by its own energy and its own frequency. With that assumption in place, Einstein sets up the situation that will squeeze the truth out of the light. He imagines the total amount of energy held fixed, and the total volume held fixed, but he allows the energy to be moved around between the different bands. He can take a little energy out of one band and put it into another, as long as the total stays the same. And now he asks the decisive question. Of all the possible ways to distribute a fixed total energy among the bands, which distribution is the one that nature actually chooses when the radiation settles into thermal equilibrium? The answer comes straight from everything we said about entropy. Thermal equilibrium is the state of maximum entropy. The arrangement there are the most ways to be in. So the equilibrium distribution of energy among the bands is precisely the one that makes the total entropy as large as it can possibly be. And this gives Einstein a powerful lever, because there is a well-known feature of any quantity at its maximum. Think of a ball resting at the very bottom of a valley. Right at the lowest point, the ground is momentarily flat. If you nudge the ball a tiny bit in either direction, its height barely changes at first, because you are at the bottom. The same is true of entropy at equilibrium. Because the entropy is at its maximum, any tiny reshuffling of energy between the bands leaves the total entropy essentially unchanged. If some small transfer of energy could increase the entropy, then the system was not yet at its maximum, not yet at equilibrium, and it would spontaneously make that transfer. So at true equilibrium, no small transfer can raise the entropy. it is already as high as it goes. Einstein turns this into something concrete with a simple thought. Pick any two bands, one at a lower frequency, one at a higher one. Take a tiny sliver of energy out of the second band and move it into the first. The total energy has not changed because we only moved it, but the entropy of the first band goes up a little, since it gained energy, and the entropy of the second band goes down a little, since it lost energy. The net change in total entropy is the gain from the first band minus the loss from the second. And we just established that at equilibrium, this net change must be zero for any such transfer. The only way the gain can exactly cancel the loss for every possible pair of bands is if there is some quantity that is the same in every single band. That quantity is the rate at which a band's entropy rises when you add a little energy to it, the entropy gained per unit of energy added. At equilibrium, this rate must be identical across all the bands. No band can be a better place to put energy than any other, or energy would flow there to raise the total entropy. Every band, from the reddest to the most violet, shares one common value of this entropy per energy rate. And now, Einstein recognizes what that common quantity is, and it is a lovely moment of connection. In thermodynamics, there is an exact definition of temperature in terms of entropy and energy. Temperature is defined by exactly this rate, the rate at which entropy increases as you add energy, at fixed volume. When that rate is high, the temperature is low, and when it is low, the temperature is high. So the statement that every band shares the same entropy per energy rate is simply the statement that every band is at the same temperature, which, of course, it must be. The radiation is in thermal equilibrium at one temperature, and every part of it, every frequency band, shares that single temperature. Two bands at different temperatures would drive energy from one to the other until they matched. So Einstein has arrived, by pure reasoning about entropy and equilibrium, at a precise mathematical bridge, a relationship linking the entropy of the radiation, its energy, and its temperature, holding for every frequency band, and derived without assuming a single thing about what light is made of. He has built the bridge he needed. Now he is going to walk across it, carrying Wien's law in his hands, and on the far side, he is going to find something that should not have been there. He is going to find that the light has been counting all along. Part 10. The fingerprint of a crowd. Einstein now has his bridge, a relationship that ties together the entropy of the radiation, its energy, and its temperature. And he has decided which stretch of the spectrum to examine, the high-frequency region, because that is where Wien's law describes the real glow so accurately, and it is precisely the region where the old classical picture failed most catastrophically. So he takes Wien's well-tested description of how the energy is distributed at high frequencies, and he feeds it into his thermodynamic bridge, and he turns the crank. What he is doing, in effect, is using the measured behavior of the light to work out the exact form of its entropy. The energy distribution is known, from experiment through Wien. The bridge connects energy to entropy, so the entropy can be extracted. It is a piece of careful reasoning, but every step is forced. There is no guessing, no free choice, only the consequences of taking the data and the thermodynamics seriously. Along the way, he has to pin down one loose end, a constant that appears whenever you reconstruct a quantity from its rate of change, and he pins it down with a piece of physical common sense so obvious it is almost invisible. If there is no radiation present at all, there should be no entropy either. No light, no disorder to speak of, nothing to count. That single sensible requirement fixes the loose constant, and with it fixed, Einstein has a clean, complete expression for the entropy of high-frequency radiation as it depends on its energy. Now he does the thing his whole construction was built for. He asks how the entropy of a parcel of this radiation changes when you change the volume it occupies. He imagines a certain amount of light energy, at a certain frequency, first spread through one volume and then confined to a different volume, and he compares the entropy in the two cases. He is asking the light the same question you would ask a gas. When I give you more room or less, how does your disorder respond? And here comes the moment the entire story has been building toward. The moment where light quietly confesses. When Einstein works out how the entropy of the radiation changes with volume, the answer has a very particular shape. The change in entropy depends on the volume only through the logarithm of the ratio of the two volumes, scaled by the amount of energy divided by the frequency and by a constant. Now that phrase, the logarithm of the volume ratio, might not set off alarm bells for you yet, but for Einstein, it would have rung like a struck bell in a silent room. Because he had seen that exact shape before. He knew precisely where it comes from. That specific dependence of entropy on volume, a logarithm of how much the volume has changed, is the unmistakable signature of a gas of independent particles. It is what you get, and only what you get, when you have a collection of separate, countable things, each one free to roam anywhere in the available space, and you ask how the entropy of the whole collection changes as you expand or shrink their container. Let me make sure the force of this lands, because it is the crux of everything. Remember the puff of gas spreading through the room, and how its entropy depends on the volume, because there are more places for each atom to be in a bigger room. When you count that up properly for a gas of separate atoms, the entropy change comes out as a logarithm of the volume ratio multiplied by the number of atoms. The number of atoms sits right there in the formula as a plain multiplier on the logarithm. It is the count of the pieces. Now look back at what Einstein found for the light. His radiation entropy changed with volume as a logarithm of the volume ratio, multiplied by a certain quantity, the energy divided by the frequency, and a constant. The shapes are identical. The light's entropy behaves under a change of volume exactly as a gas of independent particles would. And that means the multiplier in the light's formula, the energy divided by the frequency times the constant, is playing exactly the role that the number of atoms plays for the gas. It is the count. It is telling you how many independent pieces the light behaves as though it contains. So Einstein reads it off, the way you would read the number of atoms off the gas formula. The high-frequency radiation of a given total energy behaves thermodynamically as though it is composed of some number of independent pieces, and that number is the total energy divided by a certain amount. Turn that around, and you learn the energy of a single piece. If the whole energy is shared among that many independent pieces, then each piece carries an energy equal to the frequency multiplied by a constant. And when Einstein identifies that constant, by matching Wien's description to Planck's more complete formula, it turns out to be exactly Planck's constant, the same tiny number Planck had introduced in his act of desperation. So the energy of a single piece of light is Planck's constant times the frequency. Each grain of high-frequency light carries an energy set by its color, larger for bluer light, smaller for redder, and the light of a given total energy behaves as though it is a swarm of these grains, independent of one another, like atoms in a gas. Now stop and feel what has just happened, because it is the beating heart of why we believe light is a particle, and it is nothing like the tidy textbook tale. Einstein did not assume light was made of particles. He assumed nothing of the kind. He started from the measured glow of hot objects and from the statistical meaning of entropy, both of them solid, both of them trusted, neither of them mentioning particles. He followed the reasoning honestly, step by careful step, and out the other end came a number that counts pieces, and an energy for each piece, and the whole behavior of a gas of independent grains. The granularity of light was not put in by hand. It was hiding inside the thermodynamics of a warm glow, and Einstein simply counted carefully enough to find it. The wave, when asked how its disorder responds to being given more room, answered in the voice of a crowd, "This is the discovery." Not a guess about particles to explain a lab effect, but a particle nature extracted, unwillingly, from the most fundamental principles of heat. Let me put the logic one more way, plainly, because it is the single most important step in the entire story, and it deserves to be unmistakable. Two different systems can have entropy that changes with volume in the same mathematical shape only if they are, at some fundamental level, built the same way. The logarithm of the volume ratio shape is not generic. It is the specific autograph of a collection of independent, countable pieces free to roam a space. A truly continuous field, spread smoothly through space with nothing discrete about it, would leave a different autograph, a different dependence on volume, because it has no separate pieces whose freedom to be here or there is what generates the entropy in the first place. So when Einstein found that high-frequency light leaves the countable pieces autograph, he had found something that a genuinely continuous wave simply cannot fake. The shape of the entropy is a fingerprint, and the fingerprint at the scene belonged to a crowd, not to a smooth, seamless field. This is why the argument is so much stronger than a guess. He did not propose particles and check if they fit. He found the unmistakable statistical signature of particles in data that had no particles put into it. And there is a quiet beauty in how little Einstein had to assume to reach so radical a conclusion. He used the measured glow of hot objects through Wien's law. He used the thermodynamic definition of equilibrium and temperature. And he used Boltzmann's principle, connecting entropy to the counting of arrangements. 3 inputs, every one of them established, every one of them accepted by physicists who believed light was a pure wave. From those 3 uncontroversial ingredients, and nothing else, out came a conclusion that would have been called heresy if you had stated it at the start, that light, in the high-frequency regime, behaves as though it is a gas of independent quanta. He had not smuggled the answer in. He had cornered the light with things everyone believed, and the light had confessed. And Einstein, being Einstein, was not content to leave it as an abstract thermodynamic curiosity. He wanted to know whether this swarm of light grains would do anything visible, anything you could catch in an experiment. And he realized there was already a strange, unexplained effect sitting in the laboratories of Europe, an effect about light and metal that no one could make sense of, and that his grains of light would explain in a single stroke. Part 11. The Test That Should Have Failed. Only now, far into the story, do we finally arrive at the effect that the textbooks put at the very beginning. Einstein had his grains of light, pulled from the entropy of the blackbody glow, and he went looking for a place where they would show themselves. He found it in a phenomenon that had been puzzling physicists for years, a phenomenon involving light striking metal and knocking tiny electric charges loose from its surface. The charges are electrons, and the effect of light liberating them is what we call the photoelectric effect. It had been observed, it had been measured, and it made no sense at all under the wave theory of light, which is exactly why it was the perfect place for Einstein to test his radical idea. Let us look at what the experiments actually showed, because the details are what make it so devastating for the wave picture. You shine light on a clean metal surface and watch for electrons to come flying off. The first strange thing is that whether any electrons come off at all depends on the color of the light, its frequency, and depends on it in a stark, all-or-nothing way. Start with low-frequency light, down in the red, and slowly increase the frequency. For a while, nothing happens. No electrons, no matter what. Then, as you cross a certain sharp threshold frequency, electrons suddenly begin to be emitted. Below the threshold, silence. Above it, a stream of electrons. And here is the part that should stop you cold. Below that threshold frequency, you can make the light as intense as you like, as blazingly bright as you can manage, and you can shine it for as long as you like, for hours, for days, and still not a single electron will come off. Brightness does not help. Patience does not help. If the frequency is below the threshold, the metal simply will not give up its electrons. Above the threshold, more strangeness. Now electrons do come off, and if you measure how much energy they carry as they fly away, you find that their maximum energy depends only on the frequency of the light, not on its brightness. Use a higher frequency, and the electrons come off faster, carrying more energy. But make the light brighter at the same frequency, and the electrons do not come off any faster at all. Instead, you simply get more of them, a larger number of electrons per second, each one carrying the same energy as before. So frequency controls the energy of each electron, and brightness controls how many electrons. These two knobs, which the wave theory says should be tangled together, turn out to be completely separate. Sit with how genuinely upside down this is from the wave point of view, because it is easy to nod along and miss the strangeness. In the wave picture, brightness is energy. A brighter light is a bigger wave, delivering more energy per second, and energy is what an electron needs to escape. So brightness should be the thing that matters most. Turn the light up bright enough, and surely you can blast electrons off any metal with any color of light, given enough intensity. That is the common sense wave prediction, and it is completely, flatly wrong. You can take low-frequency light and crank its brightness to blinding levels, enough to heat the metal, enough to hurt your eyes, and not one electron will leave by this effect. Meanwhile, a whisper of high-frequency light, so faint you can barely measure it, sends electrons flying instantly. Frequency, which the wave picture treats as almost incidental to the business of delivering energy, turns out to be the master switch. And brightness, which the wave picture crowns as king, turns out to control only the head count. The two things the wave theory says are the same thing, energy and intensity, have come apart in the experiment, and no amount of adjusting the wave picture can put them back together. Now, why is all of this a disaster for the wave picture of light? Think about what a wave is supposed to do. A light wave, washing over the metal, delivers its energy smoothly and continuously, spread across the whole surface, like a tide rising against a sea wall. An electron sitting in the metal should soak up that energy gradually, a little at a time, its store of energy climbing steadily, until at last it has enough to break free and escape. Under this picture, brighter light means a stronger tide, more energy delivered per second, so electrons should break free sooner and fly off faster. And crucially, light of any frequency, even low-frequency light, should eventually work, if you just make it bright enough or wait long enough, because the energy is supposed to accumulate. There should be no sharp threshold. There should just be longer and longer waiting times as you turn the frequency down. Everything the wave picture predicts is wrong. It predicts a threshold that does not exist and denies a threshold that does. Let us make the failure vivid with a real calculation, the kind Einstein and others could do on the back of an envelope, because the numbers are almost comical. Imagine a modest light source, say a 1-watt lamp, placed 3 meters away from a piece of potassium metal. The light spreads out in all directions, so by the time it reaches the metal, its energy is thinned out over the surface of a large sphere, 3 meters in radius. Work out how much of that light energy falls on a single atom's worth of surface, a tiny patch the size of an atom, and then work out how long that patch would take to collect enough energy, drop by drop, to free 1 electron from the potassium. The answer that comes out is about 90 minutes. 90 minutes. Under the wave picture, you should be able to shine your lamp on the metal, go away, make a cup of tea, come back an hour and a half later, and only then should the first electrons begin to trickle off, once enough energy has finally pooled together. That is the honest prediction of light as a continuous wave. And what actually happens? The instant the light of the right frequency touches the metal, electrons are already coming off. No delay, no 90-minute wait, no gradual pooling of energy, immediate emission. Turn the light dimmer, and you do not get a longer wait, you just get fewer electrons, but they still come off instantly. The weight that the wave picture demands simply is not there. Now watch how completely Einstein's grains of light dissolve the entire puzzle, all of it, in one clean stroke. Picture the light not as a spread-out tide, but as a hail of individual grains, each one carrying an energy set by the frequency, and each one able to hand its whole energy to a single electron in a single, all-at-once collision. An electron does not sip energy slowly from a wave. It gets struck by one grain and receives that grain's entire energy in an instant. If that one grain carries enough energy to knock the electron free from the metal's grip, the electron escapes immediately, and whatever energy is left over after paying the escape cost becomes the electron's flying energy. If the grain does not carry enough energy, because the frequency is too low, then the electron cannot escape at all, and it does not matter how many such feeble grains you throw at the metal, how bright you make the light, because no single grain can do the job, and one electron is freed by one grain. There is your threshold. There is why brightness cannot force emission below it. There is why the electron's energy depends on frequency, which sets each grain's energy, and not on brightness, which only sets how many grains arrive. There is why more brightness means more electrons but not faster ones. Every single baffling feature falls into place at once. Einstein even turned this into a razor-sharp, testable prediction, the kind that can make or break a theory. He said that the maximum energy of the escaping electrons should equal the energy of one grain of light minus the fixed cost of escaping the metal. Since the grain's energy is just the frequency times Planck's constant, this means that if you plot the electron's maximum energy against the frequency of the light, you should get a perfectly straight line, and the steepness of that line should be Planck's constant itself, the very same number from the blackbody glow, showing up again in a completely different experiment. This was not a vague hope. It fixed an exact slope, an exact number, that experiments could go and measure. If the line came out straight with that slope, Einstein was right. If it did not, he was wrong. He had taken his grains of light, born in the abstract world of entropy and thermodynamics, and staked them on a concrete prediction about electrons flying off a metal plate. Now it was up to the experimenters. And the experimenter who took up the challenge did so not to prove Einstein right, but because he was absolutely certain he could prove Einstein wrong. Part 12. The verdict nobody wanted to believe. The man who set out to test Einstein's prediction was an American physicist named Robert Millikan, and it is important to understand his state of mind because it tells you everything about how physics really received the idea of the light grain. Millikan was one of the finest experimenters of his generation, meticulous, relentless, a builder of beautiful apparatus. And he thought Einstein's light quantum hypothesis was wrong, not just unproven, wrong. He found the idea that light comes in grains to be a reckless betrayal of everything the wave theory had established, and he said so in the plainest terms, calling it a bold, not to say reckless, hypothesis that flew in the face of the thoroughly established facts of interference. Remember, the wave theory was not some flimsy guess. It was Maxwell's cathedral, confirmed by a century of optics, by every interference pattern and diffraction fringe ever measured. To Millikan, and to nearly everyone else, abandoning it for grains of light seemed like abandoning reason itself. So Millikan did what a great experimenter does, with a hypothesis he distrusts. He set out to test it to death. He spent the better part of a decade, nearly 10 years, building ever more careful apparatus to measure the photoelectric effect precisely, to plot the energy of the escaping electrons against the frequency of the light, and to show, as he fully expected, that Einstein's neat, straight-line prediction would fail. The work was extraordinarily demanding. He had to prepare pristine metal surfaces, scraping them clean inside a vacuum so they would not tarnish, controlling for every stray effect, measuring tiny voltages with great precision. He poured his considerable skill into the effort, and he did it in the honest hope of proving the light grain to be a fantasy. And his own experiments betrayed him. Year after year, the data came in, and year after year, they matched Einstein's prediction. The relationship between the electron's energy and the frequency of the light was a straight line, exactly as Einstein had said, and the slope of that line was Planck's constant, the same value that came from the blackbody glow, reproduced now in the behavior of electrons flying off metal. By around the year 1915, Millikan had the decisive results, and in his paper, published the following year, he reported them, a direct measurement of Planck's constant from the photoelectric effect, in close agreement with Einstein's equation. He had built the machine to bury the light quantum, and the machine had instead handed him the most precise confirmation of it yet obtained. Here is the part that reveals just how hard it is for even the best scientists to change their picture of the world. Millikan confirmed the equation to the decimal, and he still did not believe the theory behind it. He accepted that Einstein's formula worked, that it predicted his data perfectly, and yet he continued to resist the physical idea of light as grains, treating the success of the equation as some kind of puzzle to be explained away, rather than as proof of the grains. He had verified the prediction and rejected the premise, an almost impossible mental balancing act, holding the correct equation in one hand while pushing away the picture that had produced it with the other. He was not being foolish. He was being human, and he was being loyal to a wave theory that had earned that loyalty 1,000 times over. But it shows you something profound about belief in science. Confirming a formula and accepting what it means are two very different acts, and the second can lag far behind the first. There is a lesson buried in Millikan's discomfort that is easy to miss if you rush past it to the triumph. We tend to imagine that scientists follow the evidence wherever it leads, coolly updating their beliefs the moment the data comes in. The real story is messier and more honest than that, and Millikan is the proof. Here was a man of the highest integrity, who did the experiment correctly, reported his results faithfully, and confirmed a prediction he had hoped to demolish, and who still could not make himself believe the idea behind it. That is not a failure of character. It is what it actually feels like to have your picture of the world contradicted by your own hands. A single confirmed equation does not overturn a century of successful wave physics, and it should not. Millikan's resistance was, in its way, a kind of intellectual seriousness. He understood that accepting the light quantum meant accepting a contradiction at the heart of physics, light as wave and light as grain at the same time, and he was not willing to swallow that on the strength of one effect, however cleanly it fit. He wanted more. He wanted to be forced. And physics, in the years just ahead, was about to force him and everyone else from a direction that had nothing to do with metal plates at all. It is also worth noticing that this reluctance, this refusal to leap, is part of what makes physics trustworthy in the long run. A field that abandoned its best confirmed theories at the first surprising result would be blown about by every anomaly, chasing ghosts. The stubbornness of a Millikan or a Planck is the ballast that keeps science steady, that ensures a genuinely revolutionary idea has to prove itself over and over, from many angles, before the community reorganizes itself around it. The light quantum was resisted precisely because it was important, because accepting it was expensive, because it demanded that physicists give up a picture they had every good reason to trust. That it survived that resistance, that it kept winning confirmation after confirmation until the resistance simply ran out of ground to stand on, is what makes our belief in it so solid today. The photon was not accepted easily. It was accepted the hard way, which is the only way that lasts. And Millikan was in excellent company in his reluctance. Consider Max Planck himself, the man who had started the whole thing with his energy packets. Years after Einstein's light quantum paper, when Planck was helping to recommend the younger man for a prestigious position in the Prussian Academy of Sciences, he wrote a letter of glowing praise, calling Einstein one of the great minds of the age. And then, in that same letter, he felt the need to make an excuse for him. He wrote that the fact that Einstein might sometimes have missed the mark in his speculations, as, for example, in his hypothesis of light quanta, should not be held too much against him. Read that again. The greatest physicists of the day thought that the light quantum, the idea that would win a Nobel Prize and help launch all of quantum physics, was Einstein's embarrassing misstep, a youthful overreach to be politely forgiven. Even Einstein's admirers could not follow him here. The grain of light was a step too far. The reluctance even shows in the way Einstein was finally honored. When he was awarded the Nobel Prize, the citation was worded with great care. It did not celebrate the light quantum. It did not endorse the idea that light is made of particles. It praised him for his services to theoretical physics, and, especially, for his discovery of the law of the photoelectric effect. The law, notice, the equation, the straight line with its slope. The committee was willing to honor the formula that Millikan had confirmed. It was not willing to bless the physical picture behind it. The equation was safe. The photon was still too dangerous to name. So the prize was given for the prediction, while the prediction's meaning was held at arm's length. A monument built to a discovery whose true nature the builders were not yet ready to accept. And that gap, between the accepted equation and the resisted idea, would only be closed by more evidence. Evidence of a kind even harder to argue with, arriving from a completely different direction. Part 13. Why we believe, and what we still cannot see. The idea of the light grain, which we now call the photon, was not finally accepted because it was elegant, or because Einstein was famous, or because it fit comfortably with the old picture of light. It was accepted because experiment, again and again, from different directions, forced physics to confront it, until there was no honest way left to refuse. Millikan's photoelectric measurements were one road, but the road that finally closed the matter came from a young American physicist named Arthur Compton in the early 1920s, and it did something the photoelectric effect could not quite do on its own. It showed the grain of light behaving like a genuine particle in a collision, carrying not just energy but momentum, striking an electron and bouncing off it like one billiard ball striking another. Compton was studying what happens when high-frequency light, X-rays, scatters off electrons. He found that the scattered light came off with a lower frequency than it went in, and that the exact change in frequency depended on the angle in a very particular way, a way that made no sense if light were a spread-out wave, but made perfect sense if light were a stream of grains, each one carrying a definite momentum, colliding with an electron and handing over some of that momentum in the collision. The grain of light was not just a bookkeeping device for energy exchange. It could hit things. It could recoil. It behaved, in the collision, like a particle with a momentum, obeying the same collision rules that govern the impact of ordinary objects. After Compton, the resistance broke. By the middle of the 1920s, the photon was no longer Einstein's embarrassing hypothesis. It was an accepted part of physics. The convergence had become undeniable. 3 separate roads, the entropy of the blackbody glow, the straight line of the photoelectric effect, and the recoil of Compton's scattering, all arriving at the same conclusion from different starting points. And in the century since, the evidence has only grown. Until today, we can build detectors so sensitive that they register light one single photon at a time, catching the grains individually, one indivisible click after another, exactly as Einstein's argument demanded. So now, at last, we can answer the question we started with, cleanly and honestly. Why do we believe light is a particle? Not because of the photoelectric effect. That is the myth, the tidy backwards story, and you can set it aside for good. The photoelectric effect was a test, a confirmation, a witness called after the fact, and on its own it was never even airtight, as later physicists would point out. We believe light is a particle because of something more fundamental and stranger, because when Einstein examined the entropy of hot radiation, the disorder of a simple glow, he found that light keeps its books like a crowd. Its entropy responds to being given more room in exactly the way a gas of separate, countable pieces would, and in no other way. The granular nature of light was not proposed to explain a lab effect. It was extracted from the thermodynamics of heat itself, from the way a warm object's glow behaves, before anyone looked at a single electron. And it was extracted so rigorously, and then confirmed from so many independent directions, that no continuous wave picture could ever again account for everything at once. That convergence, from heat, from metal, from collision, from single clicks in modern detectors, is the real reason. Belief in physics is not seeing. It is convergence. Light is a particle, because too many roads lead there for it to be otherwise. And here it is worth being scrupulously fair, because there is a piece of this story that the confident textbook version leaves out. And leaving it out actually weakens the case rather than strengthening it. For decades, some serious, capable physicists argued that the photoelectric effect, taken entirely on its own, does not truly prove that light is granular. They pointed out that you can keep light as a continuous wave and instead put all the graininess into the metal, into the atoms and their electrons, which do occupy discrete energy levels and do respond in quantized jumps. Worked out carefully, this hybrid picture can reproduce the threshold and the frequency dependence surprisingly well, because it is the atom, not the light, that behaves in a lumpy way. One distinguished physicist pressed this point hard late into the 20th century, arguing that people used the word photon far too casually, and that the photoelectric effect alone was not the airtight proof everyone claimed. And he was, on that narrow point, correct. Which is precisely why the entropy argument matters so much, and why Compton's collisions mattered even more, and why the modern single photon experiments mattered most of all. Each of those closes a door that the photoelectric effect, by itself, leaves ajar. The dissenters did not overturn the photon. They did something more useful. They forced physics to find the experiments that a continuous wave truly cannot fake, and the photon passed every one of them. A belief that has survived its most capable skeptics is a stronger belief than one that was never seriously challenged. But notice what we have and have not answered, because this is where honesty requires us to stop and admit the edge of what we know. We have answered why we believe light is a particle. We have not answered what light is. And those are not the same question, because here is the thing that never goes away, the fact that sits underneath all of it like an unresolved chord. The same light that keeps its books like a crowd, that arrives one photon at a time, that recoils off electrons like a struck ball, is also, unmistakably, a wave. It still passes through two slits at once and interferes with itself. It still bends around edges and spreads into shadows. It still ripples, still diffracts, still does every wave-like thing that convinced the physicists of the 19th century so completely. We did not replace the wave with a particle. We ended up holding both, at the same time, for the same light. The photon is not a tiny ball flying through space, and it is not simply a smooth wave either. It is something for which our two available pictures, the wave and the particle, are each half right and jointly impossible. This is the honest resting place of the whole story, and it is worth sitting in the discomfort of it rather than pretending it away. Physics can predict what light will do with an accuracy that beggars belief, to more decimal places than almost anything else in all of science. We can tell you exactly how light will scatter, interfere, be absorbed, be emitted. What we cannot do is tell you what light is in the ordinary sense, the way you can say what a stone is, or a ripple on a pond. Einstein himself never made peace with it. Late in his life, decades after that revolutionary paper, he wrote that all the years of conscious brooding had brought him no closer to answering the question, what are light quanta? He said that nowadays every ordinary person thinks he knows the answer, but that he is mistaken. The man who gave us the photon went to his grave still not sure what he had discovered. So we end where the thumbnail began, with a question that now carries all the weight of the journey behind it. What is light, really? We can tell you why we believe it is a particle. We can walk you through the entropy of a glowing cavity and show you the fingerprint of the crowd. We can show you the straight line of the photoelectric effect and the recoil of Compton's collisions and the single clicks in a modern detector. We can hand you more than a century of the most confirmed physics ever assembled. And still, when you ask what light actually is, the honest answer is that it is something that has never fit inside a single human picture, something that is fully a wave and fully a swarm of grains, and somehow, impossibly, both. That gap between knowing exactly what light does and not being able to say what it is has never closed. It has only deepened and grown more beautiful the longer we look. And perhaps that is the truest thing physics can tell you about light. That the largest questions do not always end in answers. Sometimes they end in a better, quieter, more astonishing way of not knowing. Rest with that tonight. The light from your screen, from the stars, from the fire, arriving one grain at a time and rippling like water all at once, still keeping the oldest secret it has ever kept.